So hello everyone and welcome to the NESP Climate Systems Hub Access webinar. For those of you I haven't yet met, my name's Jaci Brown and I've recently stepped into the acting lead role for the Climate Systems Hub, taking over from Simon Marsland. And today we are talking about access. So that's the climate and earth systems model that Australia develops, that you're going to hear a lot about what it is and why we have it and what it can do for us, particularly with the focus on decision makers across the country increasingly needing a better understanding of climate projections information and data. It's a very timely session. The conversation has certainly changed from 10 years ago when it was, is climate change real? And it's very much now, what's it mean for me and what do I do about it? But before we begin, I'd like to acknowledge the traditional owners. The Climate Systems Hub acknowledges the traditional custodians of the land on which we live across Australia, and we pay respects to elders past, present and future, and recognise the important role traditional knowledge plays in understanding Australia's climate. For me, coming from the lands of the Muanina people in Tasmania. Please take a moment to think about the traditional owners from the lands on where you're joining from as well. But now let's set the scene and provide some background about the Climate Systems Hub webinars. So if this is your first one, a big welcome. These webinars are designed to provide an opportunity for learning and interaction with a broad range of topics and experts. We've had a lot of great presentations so far, and if you want to go back and visit some of those, they're on our website. Today's another one to be added to that list. So the webinar is being recorded. The link will be available from the website after the webinar, and we encourage you to ask questions, and you can do this at any time in the Q&A function that you should be able to see on the bottom of your screen, and they're being moderated, and we'll pass those questions on later in the session to be answered. Get in early because there'll be lots of questions. So not first in best dressed, but first in gets the moderator's attention. Without further delay, I'd like to warmly welcome our very first speaker today, Will Howard. Dr. Will Howard is the lead scientist at the Australian Government Climate Change Authority. He works across areas of climate science, emissions reduction, carbon removal, adaptation, oceans, and a range of other climate policy issues. So quite a big task there, because you can't just look at one thing these days. You have to look at a whole range of aspects of climate. Previously, Will worked as the head of science for the Office of the Chief Scientist and was the lead climate science, sorry, my team is going to beep, was lead climate scientist at the former Federal Department of Agriculture, Water and Environment, DOR, which has morphed into DQ. But over to you, Will.
Thanks, Jackie. Look, it's really great to be part of this webinar. As Jackie said, I'm the lead scientist of the Climate Change Authority, and part of our job is to advise the government on climate policy broadly, and that includes advising on climate risks and advising on what is in the future, both parts of the future that we can choose, which is the energy systems and the resilience and adaptation strategies that we can take on, but also just what can we expect. So of course it's challenging to try to plan and assess risks for the future. And so one of the things that we try to do again is to advise on physical risks, and really our only window into what does our climate future look like, what do we have to plan for, is through models like access, and we look at a whole range of models like that, but access is Australia's particular, you might say, homegrown capability. So there's two pieces to that. One is, how can we tell what's coming down the pike and what's over the horizon so that we can prepare for what's likely to happen? And again, climate models like access give us a unique, really the only window we have. They're approximations, of course, and they're constantly evolving and getting better and better. They give us that window. But there's another piece that they give us. They give us a way of evaluating different different scenarios in which some of the choices that we make determine the difference among different scenarios. So as a globe and as a nation, we can choose to make different choices around energy, around fossil fuel use, and around a range of other technologies that the models then can give us a window into what does climate look like under a low emission scenario versus a high emission scenario. And in that way, we have some means of exploring the consequences, the risks, and the opportunities of some of the choices we as a nation and we as a global society make. So from those two perspectives, I think these models are just they're irreplaceable, and um, and again, the access model is extremely important because it lets us focus on climate issues that are particular to Australia and represent risks that we need to evaluate, we need to manage that uh, other partners might not focus on as closely. So we're really privileged to have Michael and Tilo talking about our own climate change modeling capability, and I look forward to hearing what they have to say.
Thanks, Will, for setting that context. It is certainly an important thing for all of Australia. And to go into a bit more detail, I'd like to welcome Michael Grose to talk a little bit more on the climate models. Michael's a research scientist at CSIRO working in climate projections, attribution, assessment and communication. He was a lead author on the IPCC 6th Assessment Working Group 1 report. And through working with CMIP6 models and downscaling for new projections, he's working as a group leader in the National Partnership for Climate Projections, the NPCP. Michael has practical insights about the role and importance for access for analysing and communicating climate change projections for the community and, importantly, for decision makers. So that's a big task, Michael. Over to you to share with us some of those insights now. Thanks.
Thanks very much, Jackie, and thanks very much, everyone, for coming. So you're going to hear from me twice. So I'm going to have a little bit of an intro to climate models, where they came from, and the history. Then we'll hear from Tilo about access itself, and then I'll come back and talk about how access is used in climate projections in the current generation of modelling. So looking way back, more than 100 years ago, it was recognised that having a system to solve lots of equations to produce a numerical model was necessary for weather forecasting. Here is a diagram of what it might have looked like before the age of computers, with hundreds of people solving those equations in a kind of a sphere-like globe. This was from Lewis Fry Richardson's 1920-2022 paper. So even before computers, it was recognised the value of this for weather forecasting, and now modern computing kind of comes along and can do that job without needing to have this physical computer. It was also recognised, very early on that numerical models are essential for climate work and assessing and understanding the effect of human influence on the climate, including the effects from, and bringing together and integrating the effects on the atmosphere, ocean circulation, sea ice, land surfaces, processes and feedback in the carbon cycle, to simulate those processes, integrate them, and also simulate the feedbacks which are needed to fully understand the effect of human influence on our climate. That's just a kind of a schematic of the greenhouse effect, which is, of course, a big one we need to understand. So just going through a little bit of history of our knowledge about the human influence on the climate. Early on, it was, understanding what CO2 does to radiation was obviously a big part in the story. And by 1896, there was a pretty good theoretical framework of what that would do to the surface temperature of the world. A little bit later, there were some measurements and observations taken that seemed to suggest that that effect was becoming detectable. And this was kind of labelled the CO2 effect as far back as 1938 through the trends that are present in a set of weather stations. And then, but into the 1960s to the 1980s, there was a big development in climate understanding and climate modelling, and using those models to attribute, predict climate changes. And two big figures in that development are shown there, who were awarded the 2021 Nobel Prize for their work. That's Hasselmann and Manabe. And they started to really develop the foundational work for using numerical models for climate work. So what did some of these early climate modelling studies show? So right from Manabe 1970 through to the IPCC 2007, if you plot those all on top of each other and the observations that we've seen since, the global temperature change over that period is really very consistent across different generations of models, right from the earliest days through to today, with perhaps one exception. And this was a figure that was presented in the IPCC 6 assessment report. So they've had a pretty good handle on the change in global surface temperature over several decades since the start of since those models were run, that they've kind of shown that they've been valuable. And on the right is another figure from an early paper. This is looking back at a model prediction or projection made in 1989 using a coarse resolution model, and then some observations that were taken since then of what it was forecast. And you can see, well, coarse resolution, of course, some of the main features of the spatial distribution of temperature change were really very clear, such as much more warming in the large continents and the Arctic than elsewhere, and a warming minimum in the Southern Ocean. So right from the earliest days, these numerical models were shown to be very valuable for understanding and for projecting, attributing climate changes. Over the next few decades, models developed. So global modelling programs were formed, adding more components to models, going to finer spatial resolutions, producing more runs of a model, so which is a larger ensemble of simulations. That's kind of the word used for a set of model simulations. And also more models were run around the world. And this producing and running different models around the world and then bringing them together into what we call a multi-model ensemble is a really, really valuable tool to assess the range of possibilities given different attempts at doing that using models. And a really important milestone here is the coupled model intercomparison program, or CMIP. It was formed, and there's now been six phases of that CMIP program. And this really does represent a massive achievement in international collaboration to get that to form and to go forward. Something that you can do once you've got model simulations is produce very nice looking animations, and these have been produced since the 1960s. There's a couple of screenshots from a very early video that you can actually view on YouTube from Cecil Leith's general circulation model from the 1960s. And so if people say that, oh, climate animation is a recent thing, well, no, it's not really. And just on the right there is just an example of a very modern, colourful animation. This was one of the ones used in a TED talk by a well-known climate scientist, Gavin Schmidt, but I could have chosen lots of other ones as well. There's some beautiful animations to kind of show what numerical models can do in terms of resolving realistic-looking processes, including weather, land surface changes, and so on. Just clicking through. Obviously, when we have these models, a natural use for them is to explore different future scenarios. So produce climate projections under a what-if exercise. If we follow X pathway, what do we get? What's the result? And this is often phrased as a kind of a low, medium, and high kind of framework from the days of 1988, the James Hansen scenario A, B, and C. A lot of value in that straight off the bat. You know, if we follow this or this or this is the result, you know, usable for them to make decisions. And then various generations of scenarios since, which have changed in their details, but often have the same kind of framework underpinning it, which is if we follow this this pathway versus that pathway, what do we get and what does it look like and what does that mean for our decisions? And that brings us to the ACCESS model. So the Australian Community Climate and Earth System Simulator, or ACCESS, was also an amazing achievement in this area for Australia because it unified weather, ocean, climate modelling under a common platform, which has got a lot of advantages. And it built on a very solid foundation since at least 1981. So the CSIRO spectral AGCM in 1981 with just two vertical levels and so on through various generations of CSIRO modelling, including the CSIRO 4 in 1991, and then CSIRO Mark 1 through to Mark 3 and up to Mark 3.6, which was the kind of workhorse model for climate work from 1993 through to 2013, with including more layers, producing a fully coupled model, participating in CMIP phase 1 through to phase 5, adding in sea ice, land surface and aerosol and so on, but then making the leap to access. And this has been a kind of a solid, high quality model since it was first kind of developed, and has been a key member of both CMIP 5 and CMIP 6. So hopefully that set the scene for you, Tilo, to take us on more detail into access now. So thanks very much.
Super, thanks, Michael. And a nice handover to Dr. Tilo Zeihn. Tilo is the lead scientist of the Hub project that's developing access. He's a principal research scientist at CSIRO Environment. So Tilo is leading the development of this Earth System Model, or ESM, version of access. Access standing for the Australia's Community Climate and Earth System Simulator. His research interests are mainly focused on the land carbon cycle interactions and the role of the terrestrial biosphere in mitigation actions and in managing carbon. So important point there that the access model is not just about climate projections, but understanding carbon and what that balance is and where that may go in the future. So over to you, Tilo.
Thanks, Jackie, and thanks everyone for joining. So this talk is introducing the Australian Climate and Earth System Model in a bit more detail, and I will also highlight some of the important applications of the model. So continuing from Michael's introduction on the history of climate modeling, I thought it would be good to give you just a very brief summary of how a climate model works in general. So a climate model is essentially a mathematical representation of our understanding of the whole climate system. This is then implemented in a computer code or in a computer program, and we call this a model. And a system model has additional components that represent, for example, the carbon cycle. And climate and Earth system models, they are very big. They can contain millions of lines of computer code. And although we can write and change the code on a normal computer, we need to run them on a supercomputer. And on this slide, you have a photo of Australia's most powerful supercomputer on the bottom right, which is called GARDI, and GARDI is part of the National Computational Infrastructure, and this is where we run our climate and Earth system model. So Australia is fortunate enough to have its own climate and Earth system model. It's called Access. There are many different configurations, versions, and applications of Access. Here in this talk, we will focus only on the global climate and Earth system model version. Access represents major processes or components in our Earth system, and because it is a global model, it covers the entire globe at the expense of a relatively coarse resolution, like most climate models. There is a schematic here on the right that shows some of the components that we model in Access, such as the atmosphere, oceans, land, and sea ice, and these components are interacting with each other through a so-called coupler, and that allows information to be exchanged between the different components. We also have additional components representing, for example, aerosols, atmospheric chemistry, and the carbon cycle for the land and the ocean. We don't develop all of the components for Access that you see on the slide. For example, the atmospheric component comes from the UK Met Office, but we adjust or tune the performance of those components to our needs. We are developing the land surface model component and the carbon cycle components, and this allows us to ensure that Access is tailored to what we need here in Australia in terms of our Earth system modeling capability. For example, Access is one of the very few Earth system models in the world that includes a phosphorus cycle or phosphorus limitation for the land. Why is that important? We model plants in our land surface model component, and the growth or productivity of those plants is limited by a number of factors, such as the availability of light or water, but also by nutrients such as nitrogen and phosphorus. Australia has very old soil, which is generally low in nutrients, and it is therefore important that we include those conditions or limitations as well in our model. With access, we can also focus on the regions that are important for us. For example, the Access Earth System model is one of the best performing models over the Southern Ocean. The Southern Ocean is not only an important carbon sink, it absorbs a significant amount of carbon dioxide from the atmosphere, but it also acts as a major heat sink, absorbing a large amount of the Earth's heat and distributing it around the planet. Maintaining and further developing a climate and Earth system model such as Access is a big effort, and this has been recognized in Australia by establishing a national research infrastructure for Access, the Access NRI. And the Access NRI supports Access development by providing, for example, software engineering expertise, whereas the scientific leadership and international engagements are coming mainly from partners such as CSIRO and programs such as NESP. And that's a nice segue actually into my next slide as well, which shows our international contribution. International climate research is coordinated through the World Climate Research Programme, the WCRP, and the WCRP also coordinates the Coupled Model Intercomparison Project, CMIP. And model simulations performed for CMIP underpin the Intergovernmental Panel on Climate Change, IPCC assessment reports. Australia has participated in all of the model intercomparison projects so far, and we have contributed simulation results from an Access model version to the last two CMIPs, CMIP 5 and CMIP 6, and we are planning to submit Access results to the next CMIP, CMIP 7 as well. As you can see on the map, which shows the modeling centers that participated in CMIP 6, most of the contributions come from the Northern Hemisphere. Australia is one of the very few countries in the Southern Hemisphere that maintains and further develops a climate and Earth system model. You can see that it's quite a concentrated effort in Europe and North America. However, all countries and modeling centers have their own priorities in terms of model development, in terms of model performance, the components that they include, and regions of interest. And they don't necessarily align with our priorities here in Australia. An Australian climate and Earth system model provides us with the opportunity to develop new science and new components that are important for Australia. For example, the way we manage our available land is absolutely crucial, and there is it's therefore important that we have the ability to represent this in our model as well. Implementing different land management strategies, including carbon dioxide removal in the model, will allow us to assess their effectiveness under a changing climate and the implications this might have on the future of our natural carbon sinks and other areas such as biodiversity, food production, or water security. Access provides us with the capability to run tailored simulations. For example, to support climate change projections for Australia, we ran a large ensemble of global simulations with Access, which is something that's not available from other models, and Michael will tell you a little bit more about this in a minute. We performed climate stabilization simulations that are in line with the Paris Agreement at different global warming levels of 1.5 and 2 degrees to get a better understanding of what a world at those warming levels might look like and what this means for Australia and the Southern Ocean. Access also gives us the ability to drive our own research in many different areas, for example, around extreme events, variability and change, and nature-based solutions. And it is an important research tool for our students and early career scientists. Oop, I was not the one I wanted. In the next couple of slides, I would like to highlight some of the work we have done recently with the Access model, or work that we are planning to do in the future. And to set the scene, I selected this schematic here, which shows you two different future pathways or scenarios. And on the top panel, you have the global mean temperature anomaly, and in the bottom panel, you have CO2 emissions. The key message here is that in order to stabilize global temperature at a certain level, we require at least net zero CO2 emissions. As long as we emit CO2, we will contribute to warming and global temperature will increase. It's now likely that we cannot limit global warming to 1.5 degrees, and we will therefore at least temporarily exceed this temperature level. And this is known as an overshoot. And in order to reverse this overshoot, which means bringing global temperatures down again, we need to achieve net negative emissions. And that requires deployment of carbon dioxide removal technologies at a very large scale. So we know where we are heading, but we don't really fully understand the consequences. The access model can help us to explore future emission pathways or scenarios so that we can get a better understanding of the implications of stabilizing the global temperature at a certain level and the risk of overshooting temperature levels and what that means for our region. In order to investigate the impacts of achieving net zero emissions at different points in time or at different global warming levels, we designed our own modeling framework and then set up and ran those simulations with the Access Earth System model. So these are quite unique simulations that are not available from other models, and they are not part of the coupled model intercomparison project either. The plot on the left-hand side shows you the results from those simulations for the global mean temperature anomaly. The green line represents a scenario where we continue to emit CO2 well into the future, and you can see the corresponding steep increase in temperature. In the model, we then switch to zero CO2 emissions at different points in time, which then stabilizes the temperature at different global warming levels. We have done a total of 7 simulations here with the Access model covering global warming levels from about 1.2 to 3.5 degrees. These simulations are quite long. They span 1,000 years. And the reason for this is that some processes are quite slow and we only see the implications or impacts after a long time. However, we need to know about these long-term impacts or changes because the decisions that we make now will have long-term impacts. For further analysis, I will only focus on one of the simulations here, the one that stabilizes at 1.5 degrees, and we will only use a small window marked here with a red box that says net zero underneath. And we compare this with a simulation where we continue to emit CO2, which is also marked with a red box that says next to it. So both of those windows or worlds have the same global warming level of 1.5 degrees on average, but at the regional scale, they look very different. And this is what the spatial plot on the right highlights. It shows you the difference between the two 1.5 degree worlds. One stabilized under net zero CO2 emissions and the other one with continuous CO2 emissions, so closer to what we are currently experiencing. And you can see that after switching to net zero emissions, large parts of the northern hemisphere start to cool, whereas parts of the southern hemisphere, especially the Southern Ocean, continue to warm. So this is quite concerning and not great news for us. The key message here is that although the global temperature stabilizes under net zero emissions, the regional climate continues to evolve, and we need to better understand how this will impact us. I only show temperature on this slide, but there is a lot more that we can now explore with those simulations. We can look at climate extremes and how they might change. We can look at sea ice extent. We can look at changes in the modes of variability, such as ENSO and rainfall teleconnections to Australia. We have done some of this work already, and if you're interested and would like to know more about those stabilization simulations, the reference for a paper that has all the details is provided at the bottom of the slide here. If you don't have the time to look at the paper, one of the key messages from the paper is that any delay in achieving net zero emissions may have long-lasting consequences and will make achieving low global warming levels very challenging. So in the previous slide, we looked at stabilizing the climate and how a stabilized world compares to a world where we continue to emit CO2. Here on this slide, we are looking at the implications of climate overshoots. So temporarily exceeding a certain temperature level and then returning to it at a later stage, and how this impacts the climate longer term. Again, we're using the Access Earth System model to perform those simulations, which are shown in the plot on the left. However, in this case, we are using scenarios from CMIP 6. So the first scenario is a low emission scenario, SSP 126. It's shown in the green line in the plot on the left. And this scenario leads to a small temperature overshoot before then stabilizing over the last 100 years of the simulations at around 1.8 degrees. The second scenario is an overshoot scenario, SSP 534OS, shown in the purple line. It leads to a substantial temperature overshoot before temperatures come down again and stabilize at 1.8 degrees, the same level as the other scenario. What I haven't explained yet is that the thick colored lines in the plot on the left represent an ensemble mean, whereas the thin gray lines are the individual ensemble members. And we ran a unique 40-member ensemble for each of the scenarios, and we then calculate the mean over all the ensemble members. So for each ensemble member, we run the model with the same climate forcing data, but with different initial conditions. So why do we do this? For an individual run or ensemble members, we get a lot of variability due to the different initial conditions and due to climate drivers such as ENSO. And sometimes we want to study this variability, but here in this case, we actually want to exclude this natural variability or noise to get a better understanding of the model response to external forcings. And the best approach for this is by running a large ensemble and then taking the mean over all simulations. So coming back to our scenarios, basically in both cases we'll reach 1.8 degrees at the global scale over the last 100 years of the simulation, but we are following very different pathways. We can now compare the regional climate over the period where both simulations have the same global warming level, indicated by the red box, and the regional climate looks very different, as you can see in the spatial plot on the right. The simulation with the substantial overshoot shows a cooling over the northern hemisphere, but a warming over the southern hemisphere in comparison to the simulation with the small overshoot. So this is good news for those who live in the northern hemisphere, but bad news for us. The key message is that the emission pathway we follow to reach net zero matters, and that temperature overshoots can have long-lasting impacts on the regional climate. So again, reducing emissions and achieving net zero emissions as soon as possible is crucial. There is a lot more that we need to explore, and climate and Earth system models such as Access are incredibly valuable here. For example, we need to understand what processes are reversible and at what time scale. And this is not just about temperature, but about the impact a climate overshoot has, for example, on our carbon stores, on the efficiency of our carbon sinks, and on our ecosystems as a whole. For example, results from the Access Earth System model have contributed to an international multi-model study that shows how a climate overshoot impacts marine habitats. And this study highlights that changes in ocean temperature and oxygen drive an irreversible loss in viable ocean habitats. And if you would like to know more about this, again, there is a reference for the study at the bottom of the slide. So where do we go from here with our Access model? I think there are a lot of questions that we need to answer, and some of them are listed here on the slide. Access is not the only tool that can help us to address those questions. We have a variety of tools and models available, and some are better suited to address a specific question than others. However, Access is the only model that allows us to assess everything in an integrated, coupled way, taking feedbacks, for example, due to the changing climate, and other actions into account. In order to better address those questions, we need to maintain and further develop Access. We need to bring in the latest science, capability, and the components that really matter to us. For example, if we wanted to assess long-term carbon management options, including the role of forests in Australia, we need to include dynamic vegetation, which will allow us to grow and manage forests in the model. We also need to include a fire component so that we can assess the impacts of disturbances on long-term carbon management under a changing climate. We know that we can't do everything, so we need to prioritize. We need to assess our capabilities. Can we actually do the things that we want to do? Do we have the right people with the right skills? Access model development and developing the science that goes into the model requires highly specialized skills, and most of the time you can't simply hire someone who has those skills already, which means you have to think ahead and you have to train people. So we not only need to think about the next generation access model, we also need to think about the next generation of climate scientists. And I will stop here and back to you, Jaci. Thank you.
Thanks, Tilo. Some good points about encouraging students into maths and science for the greater good of climate, but some sobering results that I think Michael is now going to expand on. Thanks, Michael.
Thanks, Jaci. Thanks, Tilo. Me again. So I'm just going to add a little bit more about the use of access amongst other models and other tools into producing and communicating climate projections for Australia in the current generation of climate modelling, which is based on the latest phase of global modelling, CMIP6. So Access CM2 and Access ESM 1.5, the two model configurations or versions that were produced and submitted to CMIP6 are really important and kind of foundational models within the CMIP6 ensemble. They have different projections because different models give slightly different answers, and they're all considered valid and useful. And particular aspects of the projections that these two access models produced is Access CM2 gives us a warming rate and a warming amount that's at the high end of what we think is plausible. It's a high warming future. So one of the important features to think about. Access ESM 1.5 for Australia shows the greatest rainfall decline and drying of the continent of almost any CM6 model. So that's a plausible dry scenario and stress test for Australia. That's an important part of the ensemble. Both of them come out very well in evaluation, both globally and regionally for use in Australia, and they were both used prominently in the IPCC 6th Assessment Report. And this coloured table shows evaluation metrics, with red being poor, blue being good across a range of different models. This is just one example of many evaluation studies of global climate models, and Access came out really very well in all of those evaluations done in this study and others, with little or no red flags for its use going into the future. Model bias and differences between the observed world and the model world is always inevitable, and we do have ways to deal with that, but Access does come out very well, and so we do think it's a usable model to use as part of the ensemble. So as I mentioned, Access ESM 1.5 produces a really important projection of a dry stress test for our water sector. Is this plausible? Well, since the model evaluates well, it does a good job of simulating the current climate. That's a good evidence that it's then producing something credible for the future. The processes behind the drying of Australia in this model are also very plausible, and it does match some of the past trends. So, for example, a study found that it was the only model who actually fully reproduces the observed rainfall decline in southwest Western Australia, which is evidence that therefore its projection is also credible. And this is just a figure from one of the papers that underpin kind of model selection and use for new climate projections in Australia, pointing out that Access ESM 1.5 shows a very brown change over the whole century, very much drying. At the bottom end of the range of change, both for areas that we're confident this thing get drier, the southwest, and also the north, where it's even the direction of change is unclear, and it shows drying there too. As Tilo mentioned, there's a large ensemble, many runs of the same model. This is very useful, especially for untangling and distinguishing climate variability through internal variability and the climate change signal and what climate change is doing, so which is also known as signal and noise. So, for example, looking at that example again of the southwest Western Australia, having 40 runs means that we can get a sample of the climate with 40 years per calendar year. So you've actually got a bigger sample of data, and you can actually account for variability versus trend. And you could look at things like it was produced in this and reported in this study here, the chances of getting a wet year, the chances of getting an above median year, or chances of getting a dry year. And you can kind of identify that and kind of track it through different scenarios for this model, decade by decade. Another aspect of having access models to draw on for climate projections is both access models were selected for downscaling. Downscaling using regional climate models adds new detail and new spatial resolution and more information about extremes at the regional scale. So it's a really, really useful and important tool here. And a multi-model regional modelling ensemble is emerging for use in Australia. And this was produced through partnership, through the Australian Climate Service, the NACLIM 2 program, and Queensland Future Climate. And Access is going to be a key member there. And we can have a really deep dive on both Access futures by having that downscaled using different models and produce those regional insights. One aspect specific to having a model here that we can use is we were able to work with Tilo and the Access team to select which ensemble member we wanted to downscale in particular, because we can't do them all because it's very computationally intensive. We selected R6. This shows a particularly notable stress test for Eastern Australia over the mid-century period. So we chose that as for a particular illustration of that, not only a drying trend, but if we get a downswing of variability over that period as well as a drying trend, then that's very notable stress test we need to kind of think about. Try another click. So, and as Tilo mentioned, it's going to be really useful for climate services and climate projections and climate planning to have these other futures that go beyond just a simple low, medium and high ongoing increasing emissions kind of framework, to have deep dives on some of these other ones that we know, other kind of types of trajectories we know we can do, we can experience, including transitioning to net zero, that long-term stabilization, emissions overshoot, and it also is a tool for exploring some of these issues that we know could be potentially very important, such as the reaching of the triggering of global climate tipping points. So, for example, coral reef die-off and the collapse of the Atlantic meridional overturning circulation. It's really useful to have a tool to apply to those science questions. And just to kind of note, another illustration of those effects that don't stop, even if emissions stop, the plot at the bottom is from that same paper that Tilo mentioned. This shows sea ice decline could likely be committed or locked in to continue decreasing into the future. But just a quick sum up of a few important points. That is, models are essential tools for looking into the future and for understanding how the climate is changing. For two purposes, or at least two: motivating global efforts to manage emissions, to kind of select which future we follow, and to inform the adaptation to the inevitable further climate change that we will experience. And to really emphasize that Access is a really important member of CMIP. So it's kind of like the different components come together like Voltron to form a whole that's greater than the sum of its parts. But Access is also really useful on its own to address questions that CMIP either haven't gotten to yet, or that aren't of interest internationally, that are of interest to Australia. And just a quick note of where some of the science is going now. So we've got a range of tools, and we are kind of moving towards optimizing the use of model ensembles, high resolution, bringing in new tools like machine learning and so on, and also extending modeling into more areas. So making that connection, including feedbacks through to ecosystems and climate and human systems, and further modeling and simulating and understanding our interconnectedness and feedbacks that exist within the climate system, the climate human system. So I'll leave it there and hand back to you. Thanks, Jackie.
Thanks, Michael. And loads of questions coming through the Q&A, but feel free to add some more, and quite a range of topics coming through the Q&A. So we'll move to that, and I'll jump through, try to get a bit of a flavour of all different ones. Tilo, going to you first. Do you have a theory on why the Southern Hemisphere is likely to keep warming even if we do stop emitting or reducing CO2? So that discrepancy you showed with the overshoot compared to stabilisation early.
Yeah, it's quite confronting when you see that. There are a number of factors that contribute to that. I think the main one is the heat capacity. So the Southern Ocean is very deep and has a very large heat capacity, and can therefore store heat and release heat for a very long time. So even if we achieve net zero emissions, the heat that's already absorbed by the Southern Ocean will continue to affect the regional and global temperatures for a very long time by releasing that stored heat. And a lot of the heat is also transported into deeper layers of the ocean. And some of the heat is transported around the globe through ocean circulation. And then again, a change in ocean circulation can reduce this heat transport which then further contributes to a warming over the Southern Ocean. So again, this is a good reminder that we need to reduce our emissions as soon as possible and reach net zero as soon as possible, because any additional heat that gets absorbed by our oceans, we have to deal with in the future. And now I guess there are other aspects that we haven't really covered here. For example, marine heat waves, impact on fisheries, impact on coral reefs, and so on. So we only looked at temperature, but the temperature has impact on other aspects as well.
And when we're building these models, are they incorporating paleoclimate data as well? How much do you dig into that real historical data in building the models?
So yes, we use a lot of data sets to evaluate the models. That's mainly over the historical period where we have measurements available, but also over the paleo period. So we run paleoclimate simulations as well, and where we then can compare against records. And that will help us to further improve the model and to, further tune the model towards agreeing with the observations.
Yeah, so pretty much everything we can get our hands on, I reckon, is being incorporated where we can, including traditional knowledge in some instances. Michael, I might throw to you. So there's a lot of focus on this 2 degrees warming, but is there much available to understand the 3 degrees and 4 degrees?
Yeah, so for climate projections for use and for understanding what it means for Australia and our various sectors and so on, we can look at climate change at 1.5, 2 degrees, the kind of Paris Agreement targets, but we have simulations that kind of continue warming and increasing through 3 degrees and 4 degrees, and we can have a look at those. So there's 2 important frameworks to look at the future. There's kind of trajectories moving forward through time under different scenarios. That's been the kind of tradition for a long time, and it's very useful. But we can also then take a snapshot and deep dive on when the world gets to those levels of global warming, what does Australia look like as well, which is now very policy relevant after the Paris Agreement. And so, but you can also then look at 3 and 4, and what does Australia look like in a 4 degree world? You know, it's pretty scary. I mean, some changes are fairly consistent, whether we get there relatively soon or a little bit later, but some things have very much that time commitment, including, as Tilo said, the Southern Ocean takes a long time to kind of equilibrate, and also sea level is kind of committed and continue to increase. So it depends, how long after you start to get to kind of sea level and so on. But yeah, no, absolutely important to understand those high-end warming scenarios as well.
Okay, thank you. I'm going to go back to Tilo and paraphrase this question a bit around the complexity of what one of these models look like. Is the Access ESM model publicly free software? If someone has their own supercomputer in the backyard, can they download it and run it?
I understand it's open source, and everything that's released by the Access NRI is available. Please correct me if that is wrong. If anyone is online who knows better, then yeah, please correct me. But my understanding is it is open source and it's available.
Yeah. And I think that's a really important aspect of what's being done here, that it's not just a CSIRO only model, that it is widely shared, and we want the community to be involved and to be running the model and providing feedback. Question back to you, Michael. Will this data be used or replaced in the Climate in Australia, replacing the RCP? So I think they mean Climate Change in Australia website.
Yeah, so it's been a little longer coming through this generation than last generation, but there is updates being planned to communicate the findings of Access and the full range of modelling. One of the reasons for the slightly longer time frame this time is because we're putting that stronger emphasis on that regional modelling to get more regional insights. So that takes a little bit longer to do that. And regional modelling, depends on CMIP. And then we need to then do another whole process of model evaluation, model simulation, and analysis to use that output as well in a combined sense. And I've noticed a couple of questions in the chat there. A lot of things happen after the model stops running. So there's a lot of analysis, evaluation, confidence assessment, and so on, and then analysis of indices, and then application kind of ready data sets, and so on, to get the full kind of picture of what these scenarios look like simulated by models. And a lot of that is kind of coming through the pipeline in various ways, and including for climate change in Australia. Yeah.
Yeah. Another one for you, Michael, which I think is a nice throw to the work of ACS. These models are very sophisticated, but they're modelling climate disasters and net zero carbon emissions. Wouldn't they be better to model human death and disasters? If you could maybe talk about that value chain of how that work happens.
Yeah, I mean, it'd be fantastic if we had a model with absolutely everything in the world, including people walking around within the model. I mean, that sounds pretty amazing, kind of a digital twin of the Earth, and maybe we'll get to that point at some point. But at the moment, we can definitely, and people do, look at those things as a downstream analysis out of the model output. So, for example, we can look at a realistically simulated heat wave in the model. We can then infer what that means for human health, and then also the statistical change in heat waves in different decades into the future, and say this has this implication for deaths and health and so on. Some things need to be in the model and are in the model because they have feedbacks to the climate itself. And so it would be great if we can get more and more of those in, but at the moment we can at least do a lot of this work as a downstream analysis out of model output.
And so that's sort of one trend. If we go to the other trend, Will, how do you see this sort of model output being picked up and used for the decisions that get made?
Look, I think, these are powerful models, and, what we're talking about here also highlights some of their limitations. They represent the physical and biogeochemical aspects of the system. They don't explicitly represent things like ecosystems. We talked about the Great Barrier Reef and coral reefs. So we can run the outputs of these type of models with ecosystem models and explore what that would mean for ecosystems. Similarly, as Michael said, they don't represent people. We talk one question about disasters. Well, disasters are a function in part of what's vulnerable and what's in the way of some of the natural hazards that these kind of models sort of point toward. So another frontier for models is integrating these physical models with representations of the distribution of, say, infrastructure, houses, communities, so that you have a better idea of simulating and understanding and anticipating the vulnerability of those, which is what makes a disaster a disaster, that it affects vulnerable people. And similarly, there's a great deal of discussion now about what are the economic implications of climate change. And again, a frontier is to be able to integrate models like these with economic models as well. All those sort of couplings and attempts to integrate contain a number of challenges, both scientific challenges, numerical challenges. How do you actually write an equation that represents some of these relationships? But then even once you have an equation, how do you then program that into a computer in a way that it will run and give you an answer in a reasonable amount of time? So those are all challenges. And I think those kind of questions, in addition to getting answers that are closer to the spatial and timescales that we're concerned about, I think those are all, to me, like the frontier of this type of modeling. And I think that's certainly what researchers are moving towards, but it's a bit on the horizon at the moment.
Thanks, Will. So we're coming to time. Thank you so much to the panel for those presentations. Really interesting and really, really relevant as always. Thanks to everyone for dialing in and the Q&A and for supporting the Climate Systems Hub. There'll be many more of these presentations, given such a positive response that we get from people wanting to attend. I hope you've learnt some good facts about climate modelling. We've got more great webinars lined up, so do subscribe to our newsletter if you'd like to know more about when they're on, or you can email info@nesp2climate, so nesp, N-E-S-P, 2 climate.com.au if you've got any suggestions for topics that you'd like us to bring to you. That's probably more relevant than what we just think we want to talk about. Please scroll through the Hub website for all the latest updates. And of course, we'd really love your feedback. So please provide this via the email in the chat, which is the same address we'll use to send out the recording. We'd really like to know if we're hitting the right mark in what you want to hear about. So thanks again to our presenters and for all the others who've been active behind the scenes to make this happen. See you next time.